Alright. Let me pull some things up. Okay. Alright, so today we're going to be doing the lecture for Lab 2. So this is going to be on the strain gauge. And, before I was planning on having we were going to go over the data reduction for Lab 1 as a class, but in the end I just made a video last night instead, and that's actually up right now. So I made a video instead kind of offline, because there's so much information thrown at you at once anyways for this data reduction that for a lot of you it's going to be hard to keep up, just because I know a lot of you guys are not as strong in MATLAB as maybe you would hope. So I have that video that's up right now, and you can kind of follow along with that video at your own pace. And of course, if you have any questions, you can go in Discord, put your question in there, and hopefully another classmate knows the answer. But if no one does, I'm in Discord too, and I can answer your questions there. But the video is really in depth, so again, maybe some of you're better in MATLAB than others, or you remember it a bit more. So you can go faster, go at your own pace for that video. But that video that I uploaded is, again, very in-depth, so you can, fast forward through it if you want. So again, the video is up right now, and I'm going to add, if you go on the scrubber here on YouTube, I'm going to add different, I don't know what you call it. I'm going to add different markers so you can scroll through it or scrub through it, and you can see what I'm doing at each point in the video. So in the beginning, I go over how to import the data, and as we go on here, let's see. So I'm importing data. It's for a while, defining some knowns. And then we get to when we're making a cell array. So again, I'm going to mark all of these different points in the video to tell you what I'm doing, and you can just kind of scrub through it for whatever you need some help on. Okay, so I'm going to update that sometime today. Okay, so all we're going to be doing in class today is doing the lecture on the strain gauge. And your memo for the first lab is going to be due from 2 weeks from today, so it's still 2 weeks from today. That's on September 30th. So I just made that assignment yesterday. So if you go to assignments, you can see memo 1, stress and strain. We'll click on that. And you can check out the deliverables that I've uploaded. And you're going to make your submission. You're going to upload it as a PDF. And your submission has to be your own work. Let's check out the deliverables. Okay, so you're going to compute the stress and strain. We go over that in the data reduction video. Next one, plot the stress strain curve over the elastic range and the entire range. So that means that we're going to have 2 graphs per material. So in the video, I go over how to graph it over the entire range. To graph it over just the elastic range, you can just, constrain how many data points that you plot. That's it. And I had a question last night. I didn't get to answer your email quite yet, but I had a question from a student on, where we're going to stop plotting for the elastic range. Because for all of our 3 materials, there's no well-defined yield point. So we do a yield strength. And, it's hard to see when that elastic range actually ends because it's a gradual change in the curve. So you can just kind of stop it where the yield strength is, okay? And again, if you have any questions, post it in the Discord, and then I'll answer there. Okay, the other thing you have to do is label some of these regions of interest. And for that, I show you how to do that in the video as well. So there's two different ways you can label things. You can use the gtext command, and that kind of allows you to actually place. You can just click where you want to have a label, or you can use the text command in MATLAB, and there you actually specify the X and Y location. Next thing is your percent error. So in the video I show you guys how to calculate the elastic modulus using this formula here. So we talked about that in our first lecture. So we're doing sigma 2 minus sigma 1 over epsilon 2 minus epsilon 1. Again, I show you how to do that in the video. So we calculate that, and then we compare it to a published value and get the percent error. And you're going to do that for the yield strength and the UTS as well. The other thing we're going to do, so I didn't do this part in the video, the percent reduction of area, but that's a very simple calculation. I mean, you can do it in MATLAB, or you can just use your calculator, I don't care, but that's a very simple calculation, just looking at the initial cross-sectional area minus the final cross-sectional area. That's the cross-sectional area of the fracture surface, divided by the original, multiply it by 100 to get a percentage. And there you go. So you do need the mapping toolbox, and I'll show you guys how to install that actually right now. I do show it in the video too though. But you need the mapping toolbox to find the intersection point of curves, and we need to find the intersection point when we're finding the yield strength. And your expected sample calculations at the end here. So that's in your appendix section, so you can check out the syllabus. Why not pull it up? Okay. Here we go. So that's in the syllabus, and make sure you guys double check the syllabus so you make sure that you're covering everything in your memo. And in this portion here for the structure and the weighting. So sample calcs, they go in the appendix section. It's a fair amount of points. So you need that for stress, strain, elastic modulus, and percent reduction cross-sectional area. That's all I'm asking for, so nothing else. And you only need one sample calc per thing here. So for stress, yeah, we had 3 materials, but I only need to see a sample calc one time. So you're going to start out symbolically where you're going to write out, stress. That's going to be sigma equals F over A. And then you're actually going to carry that out. So I want you to type that out so you can use the MATLAB, or not MATLAB, you can use the Microsoft Word equation editor and carry that out. And let's see. Oh yeah. So data. I uploaded everyone's data on the weekend, I think, for lab 1. So to do that, to access it, go to Files, then you go to Experiment 1, and then Lab Data. And so I guess I only have 3 groups here. I know I went to every computer to get the data, but I guess I actually didn't, So sorry about that. Group 1, the very first group, I guess I don't have your data. Sorry. So you can use someone else's data. I don't know how I messed that up. I guess I didn't double check. But so you can use someone else's data. The main important thing is that you guys actually did the experiment in person. So, and that you actually understand how to do the data reduction and all of that. So you can use like group 2's data. It looks like they have all of the runs and they have their data sheet. So I'll be sure, next week, once we do our second experiment, that I actually double check that I saved everyone's data. So, sorry. And for the video that I uploaded last night, I was using data from my Thursday class. Doesn't matter, just some other data. Alright, so any questions on the data reduction for lab 1? I don't know. I mean, you gotta watch the video later on, but any questions on when it's due or the formatting or anything like that? Okay. Alright, so we're just going to be doing the lecture then for the rest of class today on the strain gauge. So that's what you see here. Ours doesn't look quite as fancy as this one. Not that it really matters, it's doing the same thing. But this is a strain gauge right here. So the strain gauge, it's applied directly to the rod that you're testing. And since it's directly applied to it, we're not going to break the rod because, well, now we got to get a new strain gauge and apply it to a new rod. That's a lot of work. So we're going to apply it to a rod, and once we actually run the test next week, we're not going to break it. So we're going to just load it to where it's still within the elastic range for our rod. I think it's aluminum 6061T6 again, and we only have one material this time. Oh yeah, so I guess one more thing I want to note, when we click on this module for our second lab, I tried to link it where it would go to this module for the strain gauge, but I guess Canvas, it still takes you to this entire page for all of the modules that we have in class. But you can collapse the top one here because, we're done with that now. And if you go back home and then you click on this picture, then that should stay collapsed. So just thought I would throw that out there. All right, lecture time. So the strain gauge. All right, I gotta get my notes in view. So this is a pretty quick lecture too, because we're doing the same kind of thing as we did last week, right? Let's go back really quick. So the strain gauge, it's a different way to measure strain. And so what we're doing in this experiment that we're doing in person next week, we are still going to be using the extensometer that you see here. Of course, ours also looks a little different. So we're going to be using the extensometer, and at the same time, we're going to have the strain gauge applied to the rod that we're testing. And we're going to use the extensometer, which measures deformation. We got to convert that deformation to strain. And the strain gauge, it's going to give us the strain directly in the software that we're using, which is going to be LabVIEW. And so that's great for us, right? We don't need to do any conversions. We just got to read it off the screen, and that's it. And from that, we're going to basically compare the results that we get from both the strain gauge and the extensometer. We're going to see which one is more accurate to publish values for, again, for things like the elastic modulus. And from that, we're also going to compare, which one is easier to use in practice. Both of them might be very accurate, and it's not really, it's not going to be substantial for whether the extensometer or the strain gauge is more accurate. They can both be within an acceptable tolerance, right? So if that's the case, at that point, we're going to talk about in our memo which one is going to be more useful to use in practice. Because the extensometer might be a little harder to set up because you got to line up those blades on the rod. You got to make sure that it's centered vertically like we were doing last time. The strain gauge, you do need to set it up. You have to apply it. We aren't actually doing that ourselves, but I'm saying in practice, if you were like working at some company, you would actually have to apply the strain gauge yourself, but not too complicated. Anyways, that's what we'll talk about that a little more next week, but these are some of the deliverables that you're going to have on the second lab. All right. Next week, I mean that's this coming week. So this coming week, we're going to have, our very next class, right? We're going to be doing the experiment in person, week 5. Okay, so the strain gauge. Okay, so like we just mentioned, this is another device that we use to measure strain, but it's different than the extensometer because this is going to measure strain directly. Or maybe I shouldn't say it measures strain directly, but it's going to give us the reading for strain directly. Alright, so it's the same goal as an extensometer, at least for our case, which is getting strain in the end, but it does it in a different manner, it does it in a different way. Alright, so this whole time I've been saying that we get the strain directly, but I haven't actually really explained how the strain gauge gives us that. So it does this by measuring changes in electrical resistance, and it's going to measure that change in the electrical resistance, and it's going to convert that to strain by some fancy little formula that we're going to derive. It's not that fancy, actually. It's pretty simple. Okay, so this change in electrical resistance, it's going to be linearly proportional to the change in deformation, or the change in strain. Okay, so we're going to be going over the kind of the derivation for how this works, but I don't want you to worry about the derivation too much. We're actually only ever going to really talk about it in this lecture, so you don't need it for the memo or anything. It's just good to know like where kind of the background for how the strain gauge works by looking at the math behind it. But the most important thing that I want you to know is that the strain gauge works by measuring changes in electrical resistance, and it converts that to strain. So that's the big takeaway. Okay, so let's say that we have a rod, and on that rod we're applying tension, because that's what we're going to be doing again in the second lab. And then we have our strain gauge that is applied directly onto that rod. And what I drew in blue here is part of the strain gauge. So these are thin metal wires. Okay, and so these wires, they're going to experience strain directly. Okay, so they're going to undergo strain, and because they're undergoing strain, that's going to change the electrical resistance present in that wire. And then in the background, in our software and lab view, it's going to convert that change in the electrical resistance to strain, and it's going to tell us that directly. And so the way that these metal wires are orientated, it's in a position to maximize its kind of sensitivity to strain, but to minimize the sensitivity to any other kind of load, so like a shear load. So if it was, like in this direction, then it wouldn't be actually experiencing strain quite as much. Right? In fact, it'd be pretty negligible. And just as a little aside, if it is orientated like this, that allows the strain gauge to, to not experience much strain, but it's going to be affected. Let's say that we have, this metal wire that's still present, and we have this one. So both of those are going to experience changes in temperature the same, but their experience in strain is going to be different. So we could use both of these metal wires at the same time to basically measure how temperature is affecting our strain reading. And that's actually done in the background as well. So we're not going to cover the theory behind that today, but just a little aside. So just so you know that the strain gauge does have a way to measure the impact of temperature on it. All right, any questions so far? All right, so now we're going to get to our little derivation. It's not too bad, and I don't actually think in your solid mechanics class you go over this. I don't think you ever even talk about, ways to measure strain, being, the strain gauge or the extensometer. But I'll repeat myself. You don't need to worry about this derivation too much. It's just for your own background. Okay, so remember, we're going to measure the change in resistance of our electrical wires. And there's a change in resistance in those wires because there's a strain that's applied to it. And, from that change in that electrical resistance, we're actually going to be able to convert that directly to strain. So the resistance of our wires, we can write that out by R for resistance. That's going to be equal to the resistivity of the wire multiplied by the length of the wire all over the cross-sectional area of the wire. So that's a rho. That's not a P, it's a rho. That's the resistivity. L is the length of the wire. A is the cross-sectional area. Alright, and the resistivity, if you guys remember maybe from like your physics class and maybe honestly high school, or maybe you've talked about it in 226 when you took that nasty stuff, or maybe your circuits class too, right? The resistivity, that's a material property, so that's going to be given for our wire, and that's a material property for how much a material resists electrical current. So if there's low resistivity for a material, then electric current is going to be easily admitted or conducted through that material. Okay, so that's a known, that's a constant for us. So that's, we don't need to worry about that. We can easily access that information. And then we have the length of our wire. Well, we can measure that. And then we have the cross-sectional area of the wire. We can measure that. So we can measure the resistance of the wire that we have. Of course, that's going to be done through the software once again. So how's this resistance value going to change? Well, this is directly, these wires, they're directly applied to the rod, on the strain gauge. And once the strain is increasing because of our load being increased, then the length is going to increase because we're increasing that deformation, and the cross-sectional area is going to decrease because of that. So length is changing and the area is changing. So we have two variables that are changing. And what we want to do is we want to get this into a kind of differential. So we want to get a change in resistance, remember. So we need to do some, I wouldn't say fancy things, but what we're going to do is instead of having two variables that are changing, for simplicity, we only want one thing that's changing. So we are going to assume that the volume of the wire is constant, which isn't really true, but we're going to do that again for simplicity. So we have the length, we have the area, so we have a relationship for volume. So let's rewrite the formula that we have here, so we can get this in terms of volume. Okay, in this assumption, it's okay because, there's that change in length. The length is going to increase, the cross-sectional area is decreasing. So there's kind of like a balancing act there, but the volume, it's not, in reality, it's actually not constant, but it's fair enough to say that it is constant. So that's the assumption. So let's rewrite this now, where resistance, that's going to be equal to rho, the resistivity, multiplied by our length squared, and then all over our volume. So now, this is rewritten. So instead of having two variables that are changing, which, up top there is the length and the area, now we only have one variable that's changing, just the length, because we said that the volume is constant. Yeah. Okay. So again, we want to work where we're going to rewrite this so we get a change in resistance. So that's going to be a differential that we want to get to. So to get there, we're going to take the log of both sides here. I don't know, the last time that you talked about how to do logs, probably again, high school. Maybe not, I don't know. You don't use logs too much though. At least I don't. So take the log of both sides. And again, this might seem arbitrary, but we're doing this so we can then take the differential of that and we can get a nice kind of format. So we're going to get log of R, the log of the resistance, equals 2 log L, our length, plus log of the resistivity over the volume. All right. Now we're going to differentiate both sides, and now hopefully you can see why we took the log, okay? Because this is now going to be a good format for us where we can now have the change in resistance. Okay, so we have dr over r equals to 2 multiplied by dl over l plus 0. So the taking the derivative of log of rho over v, so our resistivity over the volume, both of those are constant. The resistivity, that's a material property, that's going to be constant. And we assume that the volume was constant. Derivative of a constant, that's going to be 0. So that's why we assumed the volume was constant, so we don't need to deal with that anymore. So now we have dr over r equals 2 times dl over l. With those, we can rewrite those as the change in resistance over the resistance equals 2 multiplied by the change in length over the length. And hey, we saw that before, the change in length over the length, the original length, that's going to be strain. I wrote epsilon L, but that's just strain. So we can rewrite it again if we want to solve for strain now, as epsilon is going to be equal to 1 over 2 multiplied by the change in resistance over the resistance. Okay, so now we have a way that we can actually calculate strain directly from our change in resistance. So strain is going to be equal to 1 over 2 multiplied by the change in resistance over the resistance of our wire. And I don't know, for the millionth time, this is done in the background, so it's done in the software. But it's good to know, what it's actually doing, right? Now, there's still something we got to talk about, which is this number, 1 over 2. So we just went through the derivation, but each strain gauge is kind of different for its sensitivity to strain. So we need a kind of calibration factor, and that calibration factor is kind of inputted, or it's present in that 1 over 2, okay? So let's write this out. Alright, so again, we showed the derivation for how we can measure strain from the change in resistance. But, in reality, it's not always going to be 1 over 2, okay? Because our wire might have, a bit of a difference in its material properties. So, all of this stuff, or there might be some kind of defects on the wire. So from factory, all these people that supply the strain gauge, they run through their own kind of calibration. And they give us something that's called a gauge factor. And this gauge factor, that's the calibration that is used, or the kind of constant. Okay, so instead of being 1/2, it might be 1/2.14. Okay, and again, these are calibrated from these manufacturers to kind of reflect each strain gauge's unique sensitivity to strain. So again, this calibration factor, it's called a gauge factor. So we can rewrite our formula for strain as epsilon equals 1/GF, which GF just meaning gauge factor, multiplied by the change in resistance over the resistance. And again, this gauge factor, that's given to us from the manufacturer. Okay, and this, it's not implying that one strain gauge is better than another necessarily. It's just that each strain gauge has its own unique sensitivity to strain. So because of that, our gauge factor is going to be different because the change in resistance for each strain gauge is different. So they're still going to measure strain the same, but they just had to be calibrated, right? That's it. So usually the gauge factor is around 2. For us, the gauge factor is 2.14. And now for the billionth time, this is all done in the background. So this calibration, it's actually applied in LabVIEW. So the lab technician Don, who knows when, but a long time ago, he went into the software in LabVIEW, put in that gauge factor that the manufacturer said that the strain gauge was, which is 2.14. And this equation, it's done in the background in a LabVIEW to give us strain directly. So we just look at a little box and it tells us the strain, and we're all happy. Alright, and that's it. So that's the strain gauge, that's how it works. To give a little recap, we have a strain gauge. Let's take a look at it again. So we have a strain gauge here. It's not going to look exactly like this, but we have this material. It's bonded directly to our metal rod, and on this material, on the strain gauge, there are these little metal wires, or it might be called metal foil. And those metal wires, once a load is applied to the rod, those metal wires, they're also going to deform at the same rate, just like the extensometer, right? So it's undergoing strain at the same rate as the wire. And because of that, because it's deforming, these metal wires, they have a change in electrical resistance. that change in electrical resistance, there's a linear relationship to strain, and we can then calculate strain. Each strain gauge has a different sensitivity to strain, so we have a calibration factor or a gauge factor for each unique strain gauge, and that's applied directly in the background. So our strain is going to be 1 over the gauge factor multiplied by the change in resistance over the resistance of the wires, and then we get our strain. So all the hard work, it's not done by us, so it's nice. Okay, any questions on the strain gauge? Okay, no? So, this is a pretty simple lecture for us, thankfully. And so remember, I guess just a few reminders for the class. We're going to be doing experiment 2, which is the strain gauge, next week. So let's see, what's the date for that? That's going to be on September 24th. Yeah. Okay, so make sure that you guys show up in person. And again, we're going to meet in class first, so that's E42. I might talk briefly about the lab. And, for all of the labs that we're doing now, I'm not going to give you that kind of in-depth demo for each group like I did before. Now you guys are familiar with the machine. And especially for this lab, it's virtually the same as the first lab. We're just using a strain gauge too. And I'll upload the procedures that Dr. Su made. I'll upload them before the lab. And you can access those by clicking on here. And I'll post it under week 5 for the lab. Or I'll put it in the file. So just like we have a folder for the first lab, I'll make a folder for the second lab. And the procedures will be there as well. And your memo that's due, your first memo that's due on September, or no, for you guys, it's due on October 1st. Okay. Alright, so don't forget your safety glasses next week, too. But that's all I had planned for today, so if you guys have any other questions, you can stick around, but if not, then you guys are free to go and you can have a good weekend, and I'll see you guys next week.
Thank you, Patrick. Have a good weekend.
Thanks. Have a good weekend. Thank you. Have a good week.
You said if we had any questions with Matt, that we could send you email or through Discord, correct?
Yeah.
All right. Awesome.
Yeah, I prefer Discord just because probably other people have the same question and it's just faster.
All right. Thank you, Professor. Have a good weekend.
You too.
Thank you, Professor. Have a good weekend.
Thanks, you too. All right, anyone else have any questions?
Quick question, Professor. I came like 5 minutes late. I think I missed when you were talking about our previous lab and how to do the write-up for that.
Okay. Yeah, so I made a video last night for the data reduction part of that, so to access that, I know it's not the write-up, but to access that data reduction video, which goes over pretty much everything that you need to look at for the lab, so click on week 3. Oh, okay, where did I put it? Oh, I put it in week 4. Okay, so you can click on this link, it'll take you to the video. But for your write-up, for that portion, go to assignments. Let me go to student view. So assignments, memo 1, it's due on October 1st. And all of the deliverables that you need for your memo, click on that and then you can see everything in here. So it looks like a lot, but most of this I went over in that video that I made last night. And then for the actual content for everything, make sure you look at the syllabus so you can see all of the different sections, right? The abstract, results, all of that. Make sure that you cover everything in all of these sections.
Perfect. Thank you so much.
Professor, as far as like the abstract, like, does it describe exactly how lengthy that should be, or should it just be descriptive enough to like give like a description or?
Yeah, so the abstract, I always forget that like a lot of people haven't written one until this class. It's usually around 200 words. It's not
Oh,
like
okay.
a hard cutoff though.
Okay, just explaining like from the beginning to end, like what we did.
Yeah, so like
Yeah.
what the experiment was, why it's important, and what the main results were.
Yeah. So you basically just for somebody who doesn't have time, they should be able to read your abstract and know everything about the experiment, like what results were there, like what.
Yeah, right.
Okay, that type of abstract. Gotcha.
Mm-hmm.
Okay.
Um, is there a way that you can upload um, like a previous lab write-up that has nothing to do with this experiment, just so we know like the format, I guess?
I would like to, but there's no other lab before this one where you guys have to do an abstract. But I can try to find some example abstracts just that are not not for my class, but just some random ones I find on the internet. I'll try to
Yeah,
do that.
that would be really helpful because at least for the first one, I want to make sure like before I turn it in, I have everything right and like how
Yeah.
it's supposed to be.
Yeah, I'll try to find one.
All right, thank you so much.
Um, so you said that there for other labs, there's also abstracts? Yeah, right?
Yeah. Every lab after this one, unless that instructor is different, but every single lab after this,
Oh,
you
I see
gotta
what
do
you're
the same
saying.
thing.
I see what you're saying now, like for future classes. Okay, I got
Yeah.
you.
Yeah.
Yeah, so it's pretty much the same for every report, right? Like everything we're doing.
Yeah.
Pretty much the
Mm-hmm.
same as the syllabus tells
Yeah.
us. Okay, awesome. Thank you.
Mm-hmm. Okay. Anyone else? All right, guys. I'll see you next week.
All right, see you next Friday. Good weekend.
You too.